Section 2.4, absolute value in open sentences. By open sentences, we just mean either equations or inequalities, which we've seen before, but not with absolute values. Today we're going to talk about how to solve equations that have absolute values, inequalities with absolute values, and we'll just talk quickly about some special cases. First, a little refresher. If we have these three things here, you see the absolute value of x equals 3, the absolute value of x equals 0, or the absolute value of x equals -4, these are three different cases here. Well, in the first case, the absolute value of x equals 3, that means that whatever is inside, once made to be positive, will have an absolute value of 3. That means that for the first one, we actually have two options. Either x is 3 or x is -3. The absolute value of each one of them will give us 3. The second example, the absolute value of x equals 0, there's only one way to take the absolute value of a number and get 0, so that one would only have one solution, which would be x equals 0. That's the only number who has an absolute value of 0. Anything positive would be larger than 0. Anything negative, absolute value of it would be greater than 0, so that's how it would work. And then finally, for the absolute value of x equals -4, it's actually an impossible situation. And so that equation would have no solution. And so what we have here is we pretty much have anytime an absolute value is in an equation, we have three possibilities. Either there's no solution, because an absolute value can't equal a negative. There's one solution, if the absolute value equals 0. Or there would be two different solutions if your absolute value equaled a positive number. So that's the most basic cases. Let's see how we would solve it with more complicated problems. All right, here we have an equation. 2 times the absolute value of 3x minus 5 plus 8 equals 20. In order to solve this, we're going to follow these 4 steps on the right. Number 1, if necessary, isolate the absolute value on the left. By isolate the absolute value, what I mean is we want to get this absolute value expression by itself on the left side of the equation. In order to do that, I'm going to move the 8 and the 2 to the other side. I solve it almost as if I'm looking at an equation 2y plus 8 equals 20. If I was to solve that equation, I know that all I would have to do is subtract 8. This means 2y equals 12. And then divide by 2, and I'd get y equals 6. Well, now that y that I had wasn't actually y. It was actually a whole expression that was an absolute value. So I'm going to put that back in here, and I'm going to look at the absolute value of 3x minus 5 equals 6. And that kind of makes sense because our original equation is saying 2 times something plus 8 would equal 20. Well, if that something is 6, which is what we're saying down here, then this is 2 times 6, which is 12, plus 8, which gives us 20. And so that's what we have to do. We have to first isolate the absolute value. We usually isolate it on the left side of the equation. You don't want to distribute the 2 in to make that 6x minus 10. Don't divide by 2 first unless you're also dividing the 8 by 2. But you just have to be careful about those things. Anyways, now that we have our equation of 3x minus 5 equals 6, we're going to move on to step 2. So I've just cleared up that a little bit. And now step 2, we want to split into 2 new equations, dropping the absolute value, and multiplying the right side by -1 in the second equation. What does that mean? All right, so we're going to split this into 2 different equations. And this is because, like I said before, if the absolute value equals a positive number, we're going to have 2 solutions. When the absolute value of x was 3, we had positive or -3. Now the way to get the absolute value of 3x minus 5 to be 6 is if 3x minus 5 equals 6, or if 3x minus 5 equals -6. And that's where I've multiplied the 6 by -1. As I mentioned here, to get negative 6. If 3x minus 5 as a group is either 6 or negative 6, its absolute value will be positive 6. So that's why we do the split. Now we just solve each equation. You can see that we're just going to add 5 a bunch of times actually. That'll leave us with 3x equals 11, 3x equals negative 1, then dividing by 3, we'll get our solutions. X equals 11 thirds, or x equals negative 1/3. Since it can't be both 11 thirds and negative 1/3, it's going to be these two. So I'm going to have those two solutions, and that's solving. That's step 3. And for step 4, I just check. Now when I check, I want to plug these back in to my original problem. I'll start with the 11 thirds. Plugging 11 thirds in for x, 3 times 11 thirds is 11. 11 minus 5 is 6. The absolute value of 6 is 6. 2 times 6 is 12. And 12 plus 8 equals 20. So it works. Negative 1/3 would be the same thing. 3 times negative 1/3 would be negative 1. Negative 1 minus 6 is negative 6. The absolute value of negative 6, however, is positive 6. 2 times 6 is 12. 12 plus 8 is 20. So both of these solutions work, and we're good to go. So that's how you solve an equation that involves an absolute value. Follow these 4 steps. Inequalities are similar, and there's just one thing that needs to change. I'm going to start by following the same process as an equation in isolating the absolute value. So I want to isolate the absolute value of x plus 4. So I can think about that as 3y minus 5 is less than 1. Add 5 to each side. It's going to give me 3y is less than 6. And dividing by 3 gives me y is less than 2. But again, that y, I'm going to plug back in the absolute value of x plus 4. So that's x, the absolute value of x plus 4 is less than 2. And that's what we have there. So we'd first isolate, and now we're going to split. So I'm just going to clean this up before I split here. Alright, so we're looking at x plus 4 is less than 2. I'm going to split into two different inequalities. The first one looks just the same as my original inequality, just without the absolute value bars. X plus 4 is less than 2. And the other one is going to be x plus 4. I'm going to multiply the 2 by negative 1, make that negative 2. And I'm actually also going to switch the inequality. Originally it's a less than, it's now going to become a greater than. And now I can solve each inequality. So I got minus 4, which gives me x is less than negative 2. And minus 4, which gives me x is greater than negative 6. Now with inequalities, I have this extra step of graphing. And so when I go to graph, I haven't thought yet about using and or. And that's going to come in just a second. I know that negative 6 would come over to the right. Negative 2 would go over to the left. And so this looks like a typical and I could certainly check in my original to see if that was the case. Because it looks like I would want an and therefore my solution would actually be from negative 6 to negative 2, not inclusive, open circles, but connected. And if I checked a number that fits in there, such as a negative 3, and I'm going to pick a negative 3 here, and I'm going to take that and plug it into my original. Negative 3 plus 4 is 1. The absolute value of 1 is 1. 3 times 1 is 3. 3 minus 5 is negative 2, and negative 2 is less than 1, so that works. Picking numbers on the right or left of this interval will not work. For example, 0. 0 plus 4 is 4. Absolute value of that is 4. 3 times 4 is 12, and 12 minus 5 is 7, which is not less than 1. Negative 10, for example, over here. negative 10 plus 4 is negative 6. Absolute value of that is 6 times 3 is 18, and 18 minus 5 is 13, which is not less than 1. So none of those work, which is okay, because we thought that they'd work just in here. So this is an and there's a couple of ways that we could talk about that, but there's a shortcut that we're going to focus on for now, and that's mentioned in step 2. I'm going to use Gorland, which is a little phrase there. I'll talk about more in class. But Gorland tells us what to use. If our original inequality right before the split is a less than starts with L, we're going to use and. If it was a greater than, again, this is right before the split, greater than starts with G, we'd use or. So in this case, for my solution, I would actually say that x is less than negative 2 and x is greater than negative 6. And if that's the case, then what we're looking at is this yellow bar down here, from negative 6 to negative 2. And we've already talked about the checks, so you could go from there. If this was a greater than 2, then we would have a typical or situation. Actually, these would both go out just in the opposite directions. But that's how you solve inequalities, using absolute values. Hope this makes sense. Okay, so just before we go, we've got 4 special cases where you don't have to do too much work. This will be something that'll help you out a little bit. First of all, if you have an absolute value equaling 0, remember back to the first page, there's only one situation there. So you only have one way to get there, and that's to make the inside 0. So you don't actually have to do the split if it equals 0. If you went ahead and tried to solve that in 2 different ways, you'd have x minus 3 equals 0 and x minus 3 equals negative 0. It's just the same equation. So don't solve it twice. Just use x equals 3 as your one solution. Now this next one is great because it's really convenient. There's no work to be done. An absolute value, we know, can never equal a negative. So if you have an absolute value isolated and it's supposed to equal a negative, you can stop right away and do no more work, because we know that it will have no solution. For the third example, now with inequalities here, we have an absolute value greater than negative 4. Well, we know that every absolute value is going to be 0 or positive. So no matter what you plug in here, you're going to get a number that's greater than negative 4, because the absolute value will always be 0 or higher. So when you have an absolute value that's greater than a negative, or greater than or equal to 0, this would also work as well, you know that you're going to have anything as a possibility. And so you can say all real numbers. Remember, we don't say infinitely many solutions, because with inequalities, infinitely many solutions can just be all numbers greater than 2. But that doesn't mean all real numbers here. And then finally, the last one, we have an absolute value that's less than or equal to a negative, which we know is actually impossible. There's no way an absolute value could be less than a negative, let alone equal to 1. And so it's never going to happen. This would also be true if we said that it was less than 0. But in either case, it would be impossible. And so we would say that that has no solution. So for any of these problems, if you see these, don't do too much work. For the inequalities, if you went through the process of solving them and you used Gorland shortcut correctly, what you would find here is this is going to be a greater than, so this will be an or. And the number line for that will actually show you that you get all real numbers, because you'll end up having something like this. And this is for an or. We know that that means all reals. Meanwhile, a less than or equal to would be an and so for an and, we expect it to be a certain way, but if you do it, it'll end up graphing like this, which would be no solution for an and. But that's where you have to really pay attention to the and or the or pay attention to the special cases so that you don't fall into that trap. All right, it's a brief overview, but I think everything should make a decent amount of sense to you now. hopefully we can go over it a little bit more in class to clarify anything else.